All right, everybody, here we are back with our conversation about enzymes and basically how an enzyme interacts with a substrate. So I'm going to refer to this kind of as binding models because that's one of the big things that we're going to be talking about in today's lecture. But for the time being, let's go ahead and talk about the Michaelis-Menten equation. I showed this the other day, and I made some corrections to my slide, but essentially Michaelis-Menten or the Michaelis-Menten equation is used to describe basically how an enzyme and a substrate interact and when you're going to reach a certain velocity. Now, one of the ideas of the Michaelis-Menten equation is that when the enzyme is saturated, the velocity of that enzyme, so its ability to produce a product, is at its capacity, is at its maximum level. Now, when the substrate concentration is high relative to the Km, which remember the Km is the concentration where your enzyme is at half of its maximum velocity. Now, a Km, keeping in mind, is a concentration. So this is basically an idea that when the substrate concentration is very high, consider it like 20 times the concentration of the Km. So imagining that an enzyme has a Km of approximately 0.5 nanomolar. Basically, that would say that an enzyme provided with zero point 0.5 nanomolar of the substrate is at half of its maximum velocity. Now, when you give that same enzyme, let's say 10 nanomolar of the substrate concentration, so the substrate concentration is 10 nanomolar, what that means is that that enzyme has, a much larger amount of substrate, so it can be catalyzing a reaction greater than half of its Vmax. And arguably, it's at its Vmax. So Vmax is going to be where our K2, or our K2 times our enzyme concentration at a time. Now, the enzyme is not always saturated with the substrate, so we have this equation, the Michaelis-Menten equation. This is V sub 0 is equal to your Vmax times your substrate concentration divided by your Km plus your substrate concentration. Now, essentially, one way that you could look at this is I like to put numbers down. And so let's go ahead and say, what is our velocity? That's what we're looking to find out. If we're looking at an enzyme with a Vmax, I'm just going to give a nice round number of 10. And then a substrate concentration and a Km. Let's say that the Km, and I'm not going to use, well, I'll plug in some units, but ultimately it's not going to matter because the units for substrate concentration, they're effectively going to cancel out because you'll have a concentration in the numerator here and in the denominator. So those units would cancel out, meaning that the units that are left behind would be velocity, so amount per second. But we'll go ahead and plug some in. Nanomolar per second. Okay. Now, let's say that the Km for this enzyme is 3.2 millimolar. Again, the units don't really matter. Let's say that you have, in this particular experiment, you give the enzyme substrate. But you give the enzyme, let's go ahead and say 1.6 millimolar of the substrate. Now, I like to look at this and kind of anticipate the rate that the enzyme is going to be catalyzing the reaction at. So what is V sub 0? That's what we're trying to find out. Now, we know our Vmax is approximately 10 nanomolar per second. We also know that our Km is 3.2 millimolar, okay? If we give our substrate concentration of less than our Km, which remember our Km is the substrate concentration when your enzyme is catalyzing the reaction at Vmax divided by 2, or half of your Vmax. So let's plug some numbers in just to kind of, put it together. We've got 10 up top because that's our Vmax. Then we've got substrate concentration. Well, under the provided conditions, our substrate concentration is 1.6. Then what we've got is our Km, 3.2, and we're adding to that our substrate concentration, which is, again, 1.6. So effectively, this is 16 divided by 4.8. Okay, so 16 divided by 4.8 would be, plugging this into my calculator, that's going to be 3.33. Now, you might have anticipated, oh, well, we cut our substrate concentration in half, therefore our velocity would be cut in half. Not really the case. Instead, it's going to be 3.33. Our units for this would be nanomolar per second. Now, let's go with another example. Well, let's say that our Vmax, I'm going to go with some of the same units or some of the same examples. Vmax, 10 nanomolar per second. Substrate concentration equals, let's say, 55. And then let's go with a Km of 3.2. Okay, I'm going to include units here because I don't want to be completely neglectful there. But again, the units for concentrations don't really matter. The question is, what is the V sub 0? Okay, well, let's see. 3.2 millimolar is the Km. The substrate concentration that we provided is 55. So that's more than 10 times what the enzyme needs to be at half of Vmax. Now let's see how this shakes out in terms of the enzyme's initial velocity. Okay, so again, Vmax is 10. Substrate concentration in this case is 55. Then on the bottom, we have our Km, which is 3.2 plus 55. Okay, so I'm going to say 55 times 10 is 550. Okay, 550. Divided by 3.2 plus 55 is 58.2. Okay, so now 550 divided by 58.2 is 9.45. What? 9.45 units are nanomolar per second? That seems like that's wrong, but I assure you it's not. This is the way that an enzyme is going to be behaving. And to visualize this equation right here explains our graph, where we're kind of never, much like our 100% saturated hemoglobin, we're never going to reach our Vmax. I mean, we're effectively there because you've given more than 10 times the concentration of the substrate that the enzyme needs. But, if I continue to do this example where I continue to creep up that substrate concentration, we're just going to be like here, or here, or here, or here. We're going to be under our Vmax. Okay, so now what we need to look at is another representation of the same data, but it's a kind of more user-friendly representation. So this Lineweaver-Burk, or double reciprocal plot, effectively is taking that same data that the Michaelis-Menten plot gives you, which, as you see it plotted, it's not linear. And what the Lineweaver-Burke plot does is converts that to make it more, like I said, friendly, to make it a linear plot. Now, the important parameters on a Lineweaver-Burke plot and the important places to look at on a Lineweaver-Burke plot are a little bit different from a Michaelis-Menten plot. Over here on the left-hand side, I'm going to label it as an MM plot. What's on this is you can see, well, where your maximum velocity kind of tapers off. That's labeled our Vmax. Now, if we were to look at the Km, what we would do is we would take half of the Vmax and figure out a coordinate and say, okay, well, here is the Km. Okay, so the difference is that on a Lineweaver-Burke double reciprocal plot, you have intercepts. So where your data has been made into linear form, you have a y equals mx plus b equation for a line. Now, where that data and the line of best fit from that data intersects the y-axis, that is equal to 1 over Vmax. So if you saw that the y-intercept here was 2, you'd be able to say 2 equals 1 over Vmax, and then come up with, well, Vmax equals 1/2. Okay. Now, similarly, on the x-axis, you can see that this is going to be a negative value. So this line intersecting that x-axis there, let's say that that equals 3. -3 is equal to -1 over Km. When you do the rearrangement of the algebra, you will get that Km is equal to 1 over 3. Okay, so that's how you'd plot that and calculate these Km and Vmaxes from this. Now, a benefit to a Lineweaver-Burke plot is that it's a little bit more precise than a Michaelis-Menten plot whenever you're coming up with your Km and your Vmax, because your Km and your Vmax in a Michaelis-Menten plot is a little bit more of a estimation than, say, using the plotted data to find a precise measurement. So that's one of the benefits and one of the kind of justifications or rationales as to why you would want to use a double reciprocal plot over a Michaelis-Menten plot. And here's some example numbers placed in, just like how I did those. Now, next up, we were talking about binding, and this was actually something that was addressed in Wednesday's lecture, where we talked about basically binding models. And, we had 2 substrates that would produce 1 product, or 2 substrates that would produce 2 products. There's a series of reactions that are bi-substrate reactions. Now, when we look back at either a Michaelis-Menten or a Lineweaver-Burke plot, we're really only looking at 1 substrate. So then how do you get a Michaelis-Menten or a Lineweaver-Burke plot to match when you have 2 substrates? Well, the Michaelis-Menten model of enzyme kinetics was derived for a single substrate. Okay, makes sense. So there's nothing wrong about that. But how do you kind of contort it? Well, the majority of enzymes actually have multiple substrates and products. And so you have to be able to kind of fit these bi-substrate reactions to a unisubstrate Michaelis-Menten model. Now, bi-substrate reactions account for about 60% of known enzyme reactions, and many of these reactions are transferase reactions or oxidation reduction reactions. Now, how do we actually get it to look like, well, a single substrate reaction? When we're performing kinetic analysis of a substrate by determining the rate at various substrate concentrations, well, we effectively get to starting with the substrate concentration being less, considerably less than the Km, and then we give a range all the way to considerably higher than the Km. Now, to make a bi-substrate reaction perform like a unisubstrate reaction, we keep the concentration of one substrate at saturation while studying the other substrate. So then effectively what you're going to do is you're going to saturate with one reactant and vary with a second reactant. And then you switch. So you can determine kinetic parameters for both of your individual substrates. Now, what we want to look at here is substrate addition and product release. Okay. The order of substrate addition and product release in most enzyme reactions follows two reaction mechanisms. It's either sequential or it's a ping pong reaction. Now, a sequential reaction is that all substrates must bind to the enzyme before the reaction occurs and a product is released. So let's use my left hand as an enzyme. And I've got this vitamin, vitamin D, and then I've got this other substrate. So a sequential reaction looks like this. Substrate 1, substrate 2. Okay? So both substrate reactions, or sorry, both substrates have bound. And now we're going to compare that to a ping pong reaction. A ping pong reaction is substrate number 1 binds. Product number 1 is released. Substrate number 2 binds. Product number 2 is released. So there's kind of that volleying. You send a substrate over, I'll send a product back. Now you send a substrate over, send a product back. Now, important is that these are two different substrates. Okay, so now let's go back to the sequential reaction. The sequential reaction has two different models. Either the sequence matters or it doesn't. Now, in the ordered sequential reaction, an ordered sequential reaction would be timing cube binds first, vitamin D binds second, every single time this reaction is completed. And then products are released in a particular sequence. The random sequential reaction is where, well, one time the enzyme, let's say round 1, the enzyme gets timing cube, then it gets vitamin D, and it releases products in that particular order. Then in round 2, same enzyme is going to take vitamin D first and then timing cube, and it's going to release them in a different sequence. So that's your random sequential reaction, and the ordered sequential reaction has to follow a specific sequence. Now, to look at what that looks like, or to visualize that, we use this plot right here. This is using our Cleland nomenclature, and we kind of think about it as like a little bit of a timeline. So you could think about this as start, or I like to think about this as start, and this is finish. Now, at the start, you've got your free enzyme. Substrate A binds, and then you have a complex between your enzyme and your substrate. And whenever that has happened, it's almost like A has made space so that now substrate B can bind. And when substrate B binds, now you have the EAB complex. So that this is a bisubstrate reaction. Both substrates are bound, and now you can generate your products. Now your products, P and Q, okay, those are going to be generated and they're going to be released in a specific sequence. Now, one thing that I've had people kind of get not fixated on, but curious about is, well, is A P? Does A become P and A become Q, or does A become Q? And to answer that question kind of more directly, it doesn't really matter that much what is first. So what I mean is if a substrate binds first, that doesn't mean that that's going to be the first product that's going to release. So A doesn't necessarily give rise to P, and B doesn't necessarily give rise to Q. I want you to keep that straight so that you're not confused. What's important about this is that in this particular reaction, A will always bind, then B will bind, then, I like this, your chemistry will occur, then P will be released, and then Q will be released. So there's a specific pattern. This enzyme, this kind of hypothetical enzyme here, will never bind B before it binds A, because this is the path that it's always going to take. Now, this is an ordered sequential reaction, and the reaction has a compulsory order of substrate addition and product release. It's always going to go that way. Now, comparing and contrasting that to a random sequential reaction. And if you would please look away for a second. Keep looking away. Now look back. Okay, in an ordered sequential reaction, what might happen is A might bind, and then B might bind, and then P is going to be released, and then Q is going to be released. Okay, that's one outcome of an enzyme that follows a random sequential reaction. Well, let's say round one. This is how we go, straight up the top. That's round one. Now, in round two, that enzyme might not bind A first. And if it doesn't bind A first, then it's going to bind B first. It's going to bind B, and then it's going to bind A. And you know what? This enzyme might follow the path of B, A, and then release P and Q. So this is round two. Now, let's look at one more of the multiple potential outcomes, and that would be the enzyme binds B, then it binds A, just like we saw with round two. But now what it's going to do is it's going to release Q, and then it's going to release P. So that would be our round three. Now, obviously, there's another situation where it goes in this path. And the important thing for you to recognize and appreciate about this is that the kind of organization and order of this is highly variable. The exact sequence, every single one of these is going to take place. Now, is there a preference? Do enzymes that follow this random sequential method or sequential process, is there kind of a preference or an inclination? I'm sure that there is. I'm sure that there's some steric hindrance that's going to send it down one pathway, but that's not to say that that's the only one. It might be like, yeah, 4 different outcomes. It might be 75% of them might be this, 10% might be this, and then 14% might be this, and then 1% might be this. I'm sure that it varies from enzyme to enzyme. The important point about this, though, is that you distinguish between ordered sequential and random sequential. Okay? Now, last but not least is our ping pong reaction. Now, the ping pong reaction I think is fantastic because what's important about the ping pong reaction is that you have this right here, F. I'm going to underline it. F is the alternative or alternate stable form of your enzyme. It is produced in the half reaction. Okay. Now, the way that I like to think about this is I'm going to go ahead and say that reactant A, or substrate A, I'm going to say that that is ATP. And what's going to happen is our free enzyme is going to bind ATP. And whenever it binds ATP, it's going to take the phosphate off of that third phosphate off of ATP, and it's going to give it to itself. So F is really, it's an enzyme. So it's a bunch of amino acids, but it's really E phosphorylated. Okay. Now that phosphorylated form of E, and then, sorry, let me jump back here. This is going to be the ADP, our first product that's released. Okay. So now our F, our phosphorylated form of our enzyme, has a phosphate group. And let's say that it binds, let's go ahead and say that it binds fructose. Okay, so it binds fructose, our second substrate. Binds fructose, and then you know what it does? Is it has to get back to the original E, the original enzyme. And whenever it does that, when F binds fructose, it's going to transfer that phosphate onto fructose to make, I'm just going to call it fructose 3 phosphate, just as a little bit of a different example. So this is our second product. And then what's happened is our enzyme has returned to where it started. And in the process, we had some chemistry take place. We had an intermediary unique form of our enzyme. In this case that I gave you, just this random example that I kind of made up off the cuff, is our free enzyme. Almost always, the modified enzyme has formed a covalent bond to the substrate. And this would be a prime example. Phosphate going from ATP onto our enzyme would be the formation of a covalent bond, and it would be a nice way to, I don't know, come up with a simple model. And that does happen. Enzymes do get phosphorylated and then transfers those phosphates off. Okay, so whenever you're looking at any enzyme, there's a couple of important parameters that you need to understand in order to characterize an enzyme. You've got Vmax. Okay, so that's how fast can it go. Km, that is how much of your substrate do you need? And then last but not least, what type of mechanism is it? Is it a bi-substrate reaction? If it is, it could be one of these three different, a sequential, a random, or sorry, an ordered sequential, a random sequential, or a ping pong reaction. Which one is it? Now, when it comes to characterizing enzymes, another way to, or another important parameter for understanding an enzyme is known as kcat. This kcat is also known as the turnover number. This is a measure of catalytic activity. Now, when E, your enzyme, is saturated with the substrate, the observed rate constant is the turnover number. Okay, so the turnover number, this is an important definition here. The turnover number is the number of substrate molecules converted to product per enzyme, okay? And then let's add on to that, per enzyme active site per unit of time. Okay, so there are some enzymes that have multiple active sites. You can kind of think of that about this similarly to hemoglobin. Hemoglobin has 4 oxygen binding sites. There are some enzymes that are tetramers, like hemoglobin, and they have 4, not necessarily oxygen binding sites, but they have 4 active sites where each one of those is doing something. It's producing a product. Now, in order to calculate a kcat, what you do is you take your maximum velocity of your enzyme and you divide it by, or sorry, you get your enzyme's maximum velocity and you divide it by the number of active sites that your enzyme has and the number of enzymes that you've got there. So to illustrate some of these numbers, an enzyme like catalase, well, what this is going to do is it's going to take H2O2 and produce H2O and O2, if I remember correctly, or carbonic anhydrase. It's going to take that HCO3 and produce CO2 and H2O. A kcat for each of these is either 40 million or 400,000. The larger the kcat, basically the more efficient the enzyme is. Now, a better measure of enzyme efficiency is not just, well, how many products are produced, but instead how many products are produced relative to the amount of substrate. And to calculate that into kind of more, what's the word that I'm looking for? What's the phrase? For a more frictionless calculation of catalytic efficiency, we compared kcat and km. Now, under physiological conditions, concentration of substrate is generally not saturating, or at least the saturating concentration is less than a km. Now, what I want to stress here is, well, under physiological conditions. So this is like in your body. You know, your enzyme, by virtue of it not having a huge amount of the substrate concentration, it's probably not going at maximum velocity. Can it? Yeah, absolutely. But what we want to do is we want to estimate how perfect or efficient an enzyme is. We've got kcat over km that helps us do that. Now, kcat over km is an apparent second order rate constant. What I want you guys to know about this, however, is basically how it's calculated and the significance of the value. It measures how the enzyme performs when your substrate concentration is low. Because you don't necessarily, or it's not always important physiologically to see how fast an enzyme can catalyze a reaction, but instead, sometimes you got to know, well, how about whenever the concentration is really low? Is it still kind of doing the job well? Now, the upper limit for kcat over km is the diffusion limit, the rate at which enzyme and substrate diffuse together. Now, in water, the rate constant for diffusion-controlled reactions is approximately 10 to the 9th molar seconds. Whenever we look at these different kcat over km values, we come up with numbers like this. So we look at the kcat, which is basically, jump back here. Our kcat is the catalytic activity, and then Km. Now, I want to introduce another idea on how to consider Km. And we're going to do more kcat, Km calculations later on. But Km is two things. One, it is a measure of the amount of substrate needed to reach half of maximum velocity, but it's very similar to, you guessed it, our old friend P50. This is a measure of affinity. So the lower the Km, that means the greater the affinity that your enzyme has for that substrate. So what you really want is you want a very large kcat, and then you want a very small Km, because that means that the lower that the Km is, basically the more ease with which your enzyme gets that substrate. So this is a measure of efficiency because it's comparing, well, how quickly can you get that substrate and how quickly can you turn it into the product? Okay, well, I hope this was helpful and I hope you enjoy your weekend. Um, we'll be getting into some calculations of kcat over km in our next class period. But in the meantime, I'll see you later. Have a good one.